So I'd like to start with thanking the organizers for inviting me to this wonderful symposium, and also apologize for changing my title at the very last minute. But I think this covers a bit better what I'm actually going to be talking about. This is kind of a pet project that started at OHBM last year over a very nice dumpling dinner, where I think like the conversation goes as they always go at these conferences. Someone just asks like, what are you working on? Someone says, well, I'm working on aging. Someone else says, I know a really cool method to study that. And someone else shouts, I might know a data set that we could use for this. And this is kind of like how this project evolved. I should say that project's also still very much evolving still. So if you have questions, suggestions, come find me at the poster session after this. Because I'm still very keen to get some input on this. It's definitely a developing project. The subtitle probably reflects more what we're kind of hoping to find, and I think what we're so far seeing, but the project's not finished yet, so it might be good to get your inputs on those as well. Now, there's been a lot of talk about gradients already, but I'm still going to do like a sort of a slight recapitulation of what happened last year at OHBM, because that's kind of where this project started. It started with a talk by Daniel Margulies, where he explained what gradients are, and I'm sure most of you will know that gradients is a sort of nice dimensionality reduction technique that you can use to sort of visualize connectivity patterns in a more dimensional sense. What I think is really nice about this technique, and I think what Daniel very clearly showed last year, is that it also recapitulates a sort of hierarchical organization across different dimensions. Specifically, what you can see on the figure on the right here is that like one gradient sort of nicely captures this dimension of higher order to sort of maybe lower order cognition or sensory processing, whereas this other gradient nicely recapitulates the sort of visual to somatosensory organization of functional connectivity. And what you see in the top right panel is you can also like color these by the well-known EO networks to see that there's also a hierarchical sort of transition between gradient values in that dimension. Now, when we started this project, as I was saying, someone shouted, I know a very nice data set that we can use for this, and the data set we've been using is the ChemCan data set. So it's not just a data set that I can use, it's a data set that everyone else can use here as well. And I think a lot of the research that's been presented at OHBM in the past years is really just down to people making these really nice, deeply phenotyped, multimodal imaging data sets available to everyone. So to just sort of briefly walk you through the methods, we took this ChemCan data set of, I think we ended up with about 514 individuals. We did some structural pre-processing on this data set as well, because we were doing all our analysis on surface-based approaches. So these subjects were all ran through FreeSurfer. We did some quality control. I don't think you can see the figure very clearly here, but apart from doing sort of automated quality control, all these images were also visually inspected and sort of marked by someone independent from our project, just to sort of make sure that we're actually using high-quality data. Then we went through the sort of conventional pre-processing steps for resting state, fMRI, added IC aroma to try and control for motion as much as we can. And then in all our subsequent models, we actually still use motion as a sort of confound regressor, because even though IC aroma is a very nice method and gets rid of a lot of artifacts, it might not be perfect in sort of dealing with these issues. Then we project all of these time series to the surface, and we create these connectivity matrices that I'm sure you've seen all over OHBM everywhere. And then use diffusion embedding, which is sort of the step to get these connectivity gradients to reduce the dimensionality of this like high dimensional matrix. So if we do this like in an aging cohort and we look at sort of these aging effects, what do these gradients actually look like? These are the gradients that we pop out, and to me, like at least the first sort of comforting thing to know is that the gradient that you see in the middle here is like a very nice reflection of the gradient that Daniel Margulies showed in his work where he used the Human Connectome project data. So we're sort of finding similar patterns across different data sets, which is always a big comfort. Then we can also see, like in this aging cohort, like how do these sort of gradients change, like over a healthy aging. And you probably need to squint quite a bit to see this, but roughly you can see that as a whole, the whole range of this gradient space kind of contracts across age. So we see that it becomes a little bit smaller across age. So as you go sort of up these distributions, you see that they become a little bit narrower. Now we've also tried to look at whether the bimodality, or you can look at other properties of these distributions to see how those change. Those effects might be slightly less clear. So I'm actually kind of keen to hear from people what they think would be like good metrics to actually use to quantify these distributions as we look at aging effects. Now the first thing you can also do with these gradients is sort of more conventional, like univariate approach. I think that like lots of people are using. You can just take every vertex or every node in this brain, just look to see like in which part of the brain do we find an age-related effect, and in which direction does this age-related effect go. So that's what I'm showing here in the bottom panel. You can kind of see the age-related effects after controlling for motion and sex. And what we mostly see is that actually these values in visual cortex decrease. So that kind of means that the sort of similarity within that part of the brain slightly decreases. Now this is still very much like a sort of, like I said, this is a univariate approach, and I was kind of like inspired here from one of the first talks, I think yesterday morning on Tarjakonia, where I was saying, well, people are using all these parcellation data sets, but actually, like, if we think about the brain, it's probably not that this one region just has one function. And what we're doing here is we're still kind of projecting this sort of function of was this one brain region onto one specific gradient. So it's still in a way univariate. But we can, I think, using gradients as a framework, we can take this a step further and actually sort of project these gradients into this three-dimensional space, where actually so this is across the three gradients that we're using, where actually every node in that metric actually has a value in 3 dimensions, so in multiple functions, essentially. And when we did this so this is showing our group gradient, the average across our entire data set, we can also kind of color them by the Yale networks and sort of recapitulate that differentiation between the different networks that you can see quite nicely. And then we can use the same sort of model to sort of see we saw that contraction in the network overall, but where in the network are these changes happening, and how are these changes happening relative to other networks in this three-dimensional space. So this movie, which is probably quite hard to see in this movie, but you can see that the gradient sort of changes over time a little bit. And we can quantify this simply by seeing how does the centroid of each of these Yale networks sort of move in this three-dimensional space. So this is what we're quantifying here, and just to visualize it a bit better, I've projected it into 2D space, because our brains don't deal that well with more than 2 or 3 dimensions. But basically what we're seeing, and again, sort of recapitulating some of this univariate finding that we saw before, is we mostly see that essentially the visual network seems to move inward, so it seems to become more similar to other networks, as it were. And we can see some of the other networks sort of jumbling around, but overall you can see that most of these arrows are all sort of pointing inwards a little bit. And we can quantify this a bit further. Basically what we've been looking at here, and I think this sort of pins a little bit on, I think, what the field of lifespan neuroscience has been more looking at, is thinking in terms of segregation and integration. I'm a bit hesitant to use those terms here because we use a slightly different framework. But basically what we looked at is to see within each of these Yale networks, do we see that the space across H contracts or expands, essentially. So what I'm showing here on the left-hand side is basically the t-value of to what extent the network as a whole within each network expands or contracts. So negative values means that the network contracts, positive values mean that they expand. And the distributions you see here are distributions based, it's a null distribution based on the spin test that Armin very nicely introduced in his keynote talk. I think this is quite a nice way to sort of, you can immediately spot effects in default mode and frontal parietal networks, where you can see that these two networks seem to contract as people get older. Whereas in the other networks, they don't really differentiate that much from a null model. We can also think of the same space in terms of more of a between networks thing, is where you can see how do the centers of these networks move relative to each other. And what we saw there is, and what you could kind of see in the previous movie, is you can see that the visual network, which is, I'm not sure I can use my mouse. What you can see in the previous slide, you can see that the visual network has sort of a negative distance effect towards all the other networks, meaning it's actually moving a bit closer towards all the other networks. And we can see, although this effect is much more subtle, and I don't think it will hold up to multiple comparisons, we see that the default mode and frontal parietal networks seem to move outwards a little bit. So they have a positive value, meaning the centroids kind of move away from all the other networks. Now I kind of alluded to in my title that we're also kind of want to not everything just happens in cortex, there's also subcortex, which probably has effects on this overall pattern as well. So we also decided we should probably look at how this sort of, all these changes that we see within or between different network states might be modulated by subcortical. And the first step in that is just seeing, is there any change in subcortical connectivity over age? And as you can see in this plot, which is quite a busy plot, but we can see quite widespread changes in connectivity between subcortical regions and all of the different Yale networks. We decided, just for sake of making it a bit easier, to just focus on the thalamic subcortical connectivity, which is, I think, a region that lots of other people have also sort of studied in this context. So this is a bit summary and a bit sort of saying where we want to go next and what I've shown so far. So one of the things we've seen is that we see age affects sort of this network dispersion. We've also seen that age affects subcortical connectivity. In this case, I'm showing it specifically between thalamus and the same regions that we find dispersion changes in. Now, I said in my title, it also has something to do with cognition, which I haven't really actually talked about. And luckily, I only have 2 minutes, so I don't have to talk about it too much. But we actually also looked at cognition. Specifically, we looked at the Cattell score, which is one of the many phenotypic measures we have in the data set. And perhaps unsurprisingly, and this is very well known from literature, we know that sort of there's this decline in these scores that associated with aging. But we also wanted to see, do these sort of changes that we see in the brain network actually interact with this? So the most basic thing is just to see, is there also an association between this change in network dispersion and cognition, and we find a change there as well, going into the same direction as we would expect. The next step would be, well, do we see similar changes when we look at this relation with subcortical connectivity? And I think we see the same relation again. So this is also sort of strengthening that actually all these systems sort of pin into the same framework. And then as we were sort of making these slides and sort of like putting all these arrows and trying to combine all these different findings into one coherent framework, we kind of realized what this is actually showing is a moderated mediation model. Kind of what we're interested in is we want to see, does this subcortical connectivity actually moderate this whole sort of interaction between age, a healthy brain network essentially, and cognition. Unfortunately, I think even with a sample of like 520 something subjects, it might still be quite tricky to do this in a proper model. But I think our next step would be to sort of look to see if differentiators there is like on the lower end of the age spectrum and the higher end of the age spectrum, whether you find sort of diverging moderating effects of subcortical and cortical connectivity on this framework as a whole. So with that, I'm going to leave it, and hopefully you people come up to me at the poster and ask lots of questions or have suggestions for how to improve this. And of course, I have to thank lots of collaborators who've helped me with all of this magnificent work. Without them, it would definitely not be possible.